What if the universe had turned out differently? Fred Adams pioneered the concept of what-if universes, calculating what would happen if you changed gravity, electromagnetism, or the strength of the nuclear force. Would stars still form? Could planets exist? Would atoms even exist? And ultimately, the most important question of all, would we be here even to ask such questions? His work matters to you because it explains why our universe seems so perfectly suited for life, and whether or not that's a lucky accident or maybe points to something deeper. It gives scientific weight to the idea of the multiverse as well. Not just science fiction, but as a serious cosmological possibility. It shows that the laws of nature aren't just arbitrary. They might be constrained in surprising, elegant ways. Fred Adams doesn't just study the universe, he studies all the universes that could have been, and that helps us understand why we're here at all.
The other kind of fine-tuning would be if you take a parameter and you just vary its value by a little bit, then you get a universe or something that's very different. Both of those fundamentally rely on the idea that if you change the constants a little bit, the universe doesn't work. So I think, again, back to what we said earlier, the first step in the chain is to ask the more fundamental question, the starting question, what range of parameters work?
Fred Adams, welcome all the way from Michigan by way of Pasadena. Welcome back to San Diego. You've been here a few times, and it's the first time sitting on the podcast.
Actually, the second time sitting on the podcast.
Oh, that's right. Yeah, that's true too.
But that was like 7 years ago.
That's right. Everything before COVID is a mystery to me now.
Exactly.
Yeah, exactly. Now we'll get to the multiverse. I think that's one of the most fascinating topics in all of science. Maybe concurrent with the origin of life on other planets and our planet, et cetera, which you're involved with as well, or you've written about. And not only that, you've gotten into forays with past guest and very popular guest Konstantin Batygin, working on Jupiter's, size, the deep past. That was a fascinating paper that we got to hear about. But today you're here to talk about fine-tuning and all sorts of really cool things that are related to the multiverse. But before we get there, we're speaking in early April. It's after April Fools, so everything's okay. It's after Liberation Day, so we're
liberated.
We're liberated, and I like the LI, the lithium.
And we're no longer fools. So.
We're liberated, not fools. That's right. Well, I can't necessarily say I'm not a fool. But recently, in the last few weeks, there's been a lot of interesting data coming out that seem to be in conflict with each other, if not with the standard model of cosmology. One from the Atacama Cosmology telescopes, led by my friends Mark Devlin and Suzanne Staggs, who are also on Simon's Observatory co-directors. And that seemed to be very consistent with so-called lambda CDM. But prior to that, just a week or two before that, were the DESI results. Those seem to be kind of throwing a wrench into many of the different types of works, including the work about the end of all time, and maybe suggesting there won't be eternity to wait, or we won't have a big rip, or we will have a heat death. Talk about what is the impact of DESI's new results that possibly the equation of state parameter is changing, and begin by explaining what is the equation of state, why is it so important, and what would it mean if it were changing with time via dark energy not being a constant?
Well, there's a lot of questions in there.
That's right. That's my signature move.
So the basic idea is that the universe contains some weird component, we'll say, called dark energy, cosmological constant, vacuum energy. Lots of names, and they can mean slightly different things in different contexts. But the basic idea is that empty space is not empty. It has an energy level associated with it. And that energy is in such a weird form, and it has the weird effect that it makes the universe accelerate. And in order to understand the current cosmological data, circa the year 2000, so the turn of the century, it seems that our universe is accelerating, and the simplest model that works is a cosmological model that has about 2/3 dark energy, vacuum energy, cosmological constant. Now, to 0th order, it's a constant. And if you just plug in a constant into the equations, it works pretty well. It's called a cosmological constant because when Einstein wrote down his theory of relativity 100 years ago-ish, more than 100 years ago now, he said, well, if I want to change the expansion of the universe, I'm allowed to add a constant, which was the cosmological constant. It kind of went in and out of favor with cosmological data over the next century. At the turn of this century, circa 1999, 2000, the data became good. I would say this is the short version of the story, so that it was a non-zero cosmological constant was the best model by far. Having said all that, the next question is, well, is it really a constant? Is it a constant in time? Does it vary with time? Does it vary with redshift? Does it vary with scale factor? And you could also ask, does it actually vary with position? We have no data that say it does, but you could ask that question. Mm-hmm. And the current cosmological experiments, of which DESI is one of them, are set out in part to answer that question. Does the cosmological constant, or vacuum energy, which isn't a constant necessarily, have a time dependence to it? I'm not on the experiment. I'm not an expert on the experiment. But my understanding is that there's a hint that there's a time dependence. It's not a smoking gun 12 sigma result. They want it to be in the future. At the present time, it's more of a hint that there's a possibility that there's a time dependence to it. Now, that means that if the error bars are a little bit bigger, all of the data are consistent with it being the vacuum energy being a constant cosmological constant. Now, back to the future of the universe. If you have a cosmological constant, the universe is accelerating, the future actually becomes simple. It's actually simpler than what we had to envision before, because if the cosmological constant stays robust, doesn't even have to stay constant, it just has to stay vacuum dominated, the universe will accelerate enough that it will shut down further structure formation. And then if you want to understand the future of the universe, you only have to account for the death and destruction of everything that's in our universe today. You don't have to actually calculate what comes in our horizon later and makes new stuff. So it actually makes the whole future of the universe business one step easier. Now, if the cosmological constant is time varying, that means the universe could, and probably will in the near term, continue to accelerate, just not quite as quickly. And if that's the case, then all of the future of the universe stuff remains the same. It does not have virtually any implications to it.
Where would the energy go? I mean, is it decaying? Is it converting into matter particles?
Well, those are the $1 million questions that people want to answer. It depends what physics is driving the cosmological constant. So we don't know. I mean, if the cosmological constant is just a constant, then all you get is one number, which is the value of that constant. And the experiments tell you nothing beyond that. So you have to rely on theory and other experiments to tell you. Ideally, what you would like is for something like a string theory or M theory to demand that there's a cosmological constant, and then have that same theory predict other things like proton decay or other physical things we could measure, and thereby verify said theory. We don't have any of that yet. That's the hope, that's the dream. We'd love to have enough data to have a high energy theory and have that high energy theory give us information on the cosmological constant.
Are we closer than we were? I mean, it's supposedly the greatest mismatch in the physical sciences or in the history of humanity, the so-called deviation from first principles analysis of vacuum energy density, what it could be in quantum mechanical terms, versus what we observe it to be cosmologically. As a practicing and eminent theorist, do you really believe that that's something to be embarrassed about, or is it just some other mystery that, you know, we didn't know the mass of the neutrino, or we still don't know it, or the mass of the electron for many years, but the fact that it's so low compared to, say, the Z boson, it's not embarrassing, it's just the way nature is. Where do you rank this? Is it the greatest embarrassment, as we often teach our children and our students?
Well, I don't think it's my own personal feeling, and I should preface this by saying I'm not a relativist, so I don't work on, and I'm not a string theorist, so I don't work on the cosmological constant problem for a living. So I'm one step, although I am a theorist, yes. I'm one step removed from being an expert on the question that you're asking me to be an expert on. Having said that, from that one step outside, I would say it's an issue. I wouldn't say that it's an embarrassment. Just to put the problem on the table, the problem is this. If you make a back-of-the-envelope calculation about what the vacuum energy density should be, you get basically energy density, which is the Planck mass to the fourth power. The argument is simply that the only scale we have is gravity. Gravity is given by the Planck mass. Energy density is a mass to the fourth power. That gives you a number. Then you say, well, let's look at the data. The universe is accelerating. What energy density do I need to make it accelerate? You get another number. Those two numbers are different by 120 orders of magnitude. That's the embarrassment you're talking about. And it is a sign, it's a big neon sign saying, hey, something's wrong here, clearly. And no one, I would think, would dispute that there's something interesting going on there. One thing that's clear, I think, is that if you make a calculation and it's wrong by 120 orders of magnitude, I'm going to say something controversial here.
Yeah, please.
The calculation's wrong.
Yes.
Now, how it goes wrong is where the interesting thing comes in. But clearly, if you make a calculation and you're off by 120 orders of magnitude, you probably missed something, right?
One would think.
One would think. Now, you can fudge this a little bit in the following way. We're talking about the energy density. If you talk about the energy scale, you get to take that number to the fourth root. So instead of being 120 orders of magnitude off, you're only 30 orders of magnitude off. Second, you could also argue that instead of using the Planck mass as the magic mass scale, you can use a lower mass scale, a grand unified mass scale, or maybe even something lower, depending on which version of the physics you want. We know that quantum field theory is a good theory up to and including the standard model.
Right.
So it would be a very sensible argument to say we need that energy scale to be at least bigger than what we see in accelerators, because we have seen no breakdown of it yet. That will buy you more orders of magnitude, but you still have a number of order of magnitudes off. So there's still, as you call it, an embarrassment, as I call it, an interesting issue that we need to study. And exactly how big it is, I don't know. I think that once we resolve it, then it will become clear. If you look at the example you described, if you just look at the masses of the leptons, we got 6 quarks and we got neutrinos and electrons. If you just plot them, just as little delta function spikes, they're kind of logarithmically distributed. That's actually
prime numbers.
That's actually in the review article that I'm going to talk about as the colloquium this afternoon.
Which you're graciously allowing us to broadcast as a part 2 of this episode.
Although I won't get into that issue because of time. But nonetheless, if you just look at the masses of the particles and squint your eyes enough, they're kind of logarithmically distributed. So you could ask the question, well, why is one so much lower than the other? Why aren't they all the same? Or you could ask the question, well, why are they logarithmically distributed? And of course, they're not perfectly logarithmically distributed. But if you work in log mass instead of mass as your variable, they look kind of normal by comparison. So what's the right thing to do? Answer, we do not know. So this is where physics is working. This is the frontier of physics. People are working on it, but I don't think the questions you're asking have great answers at the moment, right? We would love to have them. You know, if I actually had a great answer to your question, I would ditch this podcast and go write a paper on it. No offense, but
no, I would join you. I'd beat a path to the door.
I think we just turn off the mics and get to work, right?
So one of the things that we often hear about is that the value of the cosmological constant is somehow related to us having this conversation, whether we're able to exist. And I often hear if it was changed by just one part, and choose your favorite large number, it would actually be impossible for us, in fact, to have this conversation. This brings up the topic of fine tuning, which you are, I associate you, Mr. Fine Tuning. There's this guy, James Clear. He's Mr. Habits. There's friends of mine that do productivity, Cal Newport, other productivity people, deep work. I call you Mr. Fine Tuning. But tell me, Fred, what is fine tuning and how can it be used as a physical tool rather than just a philosophical, interesting coincidence, but nothing that we can use as physicists to test hypotheses, make predictions, and make measurements? What is fine tuning?
There's at least 2 important kinds of fine tuning that is important to, they're both important, but they're different. The first kind of fine tuning, which some people call fine tuning, is what you alluded to earlier, namely that if you look at the value of the cosmological constant we see in cosmological data, and you look at the value of the cosmological constant we calculate by taking the Planck mass to the 4th power, we get a hierarchy where the 2 numbers are different by 120 orders of magnitude. That's not exactly tuning, because you're just way off. The hierarchy is just wrong. It's a hierarchy problem. Now, one of the reasons it's called a fine-tuning problem is that when you actually get into not just the order of magnitude version of that calculation, but a more careful calculation where you try to do a quantum field theory calculation of what should be, you can take large values of vacuum energy, these large numbers to the 4th power, and then you can add other large numbers to the 4th power to cancel them. And if you take 2 large numbers with opposite sign and cancel them, and you're left with something small, in order to get something small, you have to tune that calculation carefully. So there could be tuning involved in explaining the hierarchy, if you will, but it's a different thing than the other kind of fine tuning.
Can you give me an example?
And now I'm going to give you an example of the other kind of fine tuning. The other kind of fine tuning would be if you take a parameter and you just vary its value by a little bit, then you get a universe or something that's very different. Let me give you a concrete example. Take the sun or a main sequence star, and take a number that you like the strength of gravity, the gravitational constant, what we in physics call big G. Also, whatever the Planck mass squared, if you like that. Depends on what brand of physicist you are. But nonetheless, you take G and you ask the question, by what percentage can I change G before the sun ceases to shine? Is it 1%?
Right.
Is it 10%? Is it a factor of 2? Is it a factor of 1,000,000? How much can I vary G and still have the sun be a star? And then you have to define what you mean by a star. You might want it to be a hydrostatically supported, nuclear burning, long-lived entity. That's what I think a star is.
like that, yeah.
And operationally, that means there are solutions to the stellar structure equations that give you a hydrostatically supported, long-lived, nuclear burning entity. So then you can say, well, is it fine-tuned or not? Then there's another question. Well, but how sensitive does the answer have to be to G before you call it fine-tuning? Is a factor of 2 fine-tuning, or do you need to be 1% fine-tuning? Now, in that particular case, you can vary G by about a factor of 1,000,000 and you're still good. So it's not really fine-tuned in that instance. The sun is not super dependent on the value of G. Now, the exact luminosity depends on G, but you can still have a working star with varying values of G. And if you're worried about habitability and you say, well, if I change G, the sun gets brighter, well, then I can, Earth still live? There's stars of different masses that will play the role.
And planets of different distances.
And planets of different distances. So you can vary other parameters. To cap, there's 2 issues of tuning. One is a hierarchical thing, where you have one parameter that's many orders of magnitude different than what you think you see, but we might not be that sensitive to the small value. Suppose the cosmological constant were half as big. Would we care?
No.
No. Suppose it's 10 times smaller. Would we care?
I think the issue is it was much bigger, right?
If it's
Big Bang, infinite
if
de Sitter
it's
space.
much bigger, then you would run into trouble. That leads us to the vignette that you alluded to earlier. Namely, in the late 80s, if I remember my history right, Steven Weinberg famously was working on the cosmological constant problem. And he realized that, well, if the cosmological constant is too big, you'll shut down structure formation early. So he did a calculation, and his calculation showed that if you keep everything in the universe the same and you make the cosmological constant larger, if you make it too large, then you'll shut down structure formation and we won't have a universe like our own. And if I remember right, the value that he got in his original paper was something like 500 times larger than the then current limit, which was order of magnitude the same as our current value. So it's not a 1% bigger.
No.
It's not a tune thing,
but
you can't make it too big. And you can only make it, let's say, a factor of 100 bigger if you want to be in order of magnitude land, not 120 orders of magnitude bigger. So 2 orders of magnitude versus 120, you still have this hierarchy problem. But in terms of tuning and sensitivity, you can make it 10 times larger and still have a universe that works. But you can make it 10 times smaller or 1,000,000 times smaller and have the universe work. But then there's more. You can also ask the question, why is that? Why is the universe sensitive to a large value of the cosmological constant? And the fundamental reason is something called the microwave background, which you know lots about.
Brought it here with us today.
It's right here. It's right here on this globe. So these little fluctuations, our little visual aid, are 1 part in 10 to the 5-ish, right? And you guys worry about how they vary with angular scale, but on broad brush terms, they're 1 part in 10 to the 5.
That's right.
So that means that density fluctuations in the early universe start small and then have to grow. But let's say that you had a different universe with a different cosmological constant, but you had different micro-background fluctuations. Suppose they were larger. Well, it turns out the limit goes like that amplitude cubed. So if I make the fluctuations 1 part in 10 to the 4 instead of 1 part in 10 to the 5, my limit goes up by a factor of 1,000. If I go up to 10 to the minus 3, then my limit goes up by a factor of 1,000,000. And it's already a factor of 100 larger than what we see. I can make it 1,000,000 times weaker and still have a viable universe if I'm allowed to turn the knob of making the fluctuations larger. Now, for those of us who've played with inflationary models, it's actually a whole lot easier to make a universe inflate if you only have to make the fluctuations as small as 10 to the minus 3 versus 10 to the minus 5.
Mm-hmm.
You have to work much harder to get the small fluctuations that we see in the micro background.
Right.
Which would suggest, although we don't know how probabilities, it would suggest that randomly more universes would have larger fluctuations than ours, in which case they could get away with larger cosmological constant values than ours. So that leads to a question that you're going to ask later in this talk, namely, how do you actually do the accounting of what's fine-tuning or not? Right. It depends on what you assume is given and what you are allowed to vary. So if I'm allowed to only vary the cosmological constant energy density.
Many of you are watching this on a television, and I know that if you love the cosmos as much as I do, you'll want to subscribe now. It's a little more tricky on TV, but it's well worth your time. Click down below, and don't forget to leave a thumbs up. More minds, more mysteries, more multiverse awaits you.
When we have the degree of fine-tuning is sort of phenomenon dependent, right? I mean, if we look at your classic example I always associate with you is you're tuning a radio. Old-fashioned tuning. The kids today, they don't know how to tune a radio because how do you tune in YouTube, right? How do you analogize this in terms of a radio station? Because someone say, yes, you need to get it within a few kilohertz on a megahertz scale. So is that part in a million, or is it part in 1,000? Or is it really from 0 to infinity and everywhere in between? And actually you picked out this one band that's right. Anyway, can you give your analogy? What does it mean to be fine-tuned in a way that the audience can understand if they're not familiar with?
Well, if you want to tune a radio, you need to specify the frequency of the tuner, because each radio station has a different frequency. Now, the FCC tells you what the allowed spacing of those frequencies are, because they only give licenses for so many radio stations. So in very rough orders of magnitude terms, frequencies are spaced sort of 1% of the frequency apart. Mm-hmm. So if you change your frequency by more than about 1%, you go from one station to the next, or one allowed station to the next. Not every part of the country has their radio band saturated, but if you're in a big city, you change your frequency by 1%, you go from one station to the next. So if you actually want to tune in a radio, you have to know the frequency, or the radio has to know the frequency, to about 1% accuracy. Less accuracy, so bigger error bars, will not get you your radio station. Mm-hmm. So tuning, not fine-tuning, but just tuning a radio, requires 1% accuracy. So the analogy for cosmology would be, or astrophysics would be, if you change the value of a cosmological parameter or a fundamental physics parameter, like the strength of gravity, by 1%, you would go from one universe to another, from stars that work to stars that don't work. But in the case of G and stars, we just saw that, you can change G by a factor of 1,000,000 and still have stars. That's not 1%.
No. That's right. Often the objection I hear, we've had people like Luke Barnes and others that you're familiar with, and they'll say, well, that's fine if you want one station, but actually a functioning radio means I want as many stations as are available, thanks to the courtesy of the FCC, while they still are putting out radio broadcasting licenses. So it's not really one for it's the combined probability of being able to tune every single radio station to that 1%. And isn't that now getting into we have to look at now the joint probability distribution of tuning in, let's say 30 radio stations at the 0.1%, at the 0.1%. That now seems to be, or 0.1%. That now is that factor to the 30th power, right?
Yes, if you had to tune 30 parameters all at the 1% level, then the chances of getting them all right would be a small probability. A couple things are important here. One is that it's probably not the case that we need 30 parameters to have the right values. Although we probably need maybe 10, and we can talk about that if you'd like.
Yeah. Just like the joint probability for multiple ones is analogized to multiple constants. So if there are 10, those 10, Martin Rees says 5, you says 6, you say 5. Is it essentially, dependent on the most finely tuned amongst all those parameters, or is it somehow, more complicated? Yeah, I'm trying to first of all get you to make the steelman for the case against, for the fine-tuning argument as being an issue for these types of calculations. So do we really need to tune in that many parameters? What's the minimal set of parameters that would have to be finely tuned, and which one is the most finely tuned if you had to say it's finely tuned? We already said that G is not one of them, right? It's not the most stringent one.
Okay, so
what is the most stringent?
So let's back up and let's talk about what values of the constants could vary. Okay, so one way to start is if you look at the Standard Model of particle physics, it famously has 26 free parameters in it. That includes kind of everything, the coupling constants that determine the masses of all the particles, like the mass of the bottom quark and such. But if you look at your stellar structure equations, there's not really a place for you to plug in the mass of the bottom quark. All those quarks kind of do their thing early in the early universe and are pretty much gone by the time you are working on stars.
That we care about, right?
So if you actually care about the working things in our universe today, what do you care about? Well, one way to phrase it would be this. We need the four forces of nature.
Yes.
So there has to be a coupling constant which sets the strength of gravity, sets the strength of the electromagnetic force. We call that the fine structure constant alpha, and analogous things that somehow specify the force of the strong force and the weak force. The story is a little bit complicated because those coupling constants run, as they say, which means they're functions of energy and
variable constants. So
yeah,
it always drives me crazy.
Yeah, so variable constants is a thing, but nonetheless, you have to specify somehow the strength of the four forces. So we'll start there. You need those. Now, you also have to say something about the masses of particles. I would say minimally you need to specify the mass of the electron, the mass of the up quark, and the mass of the down quark. Because the mass of the up and down quark, to remind your listeners, determines the masses of protons and neutrons. And those are important. The other quarks are, no offense to the other quarks, but they're less important for the discussion of today.
It's like every other galaxy but the Milky Way.
Yeah. So I think that from the physics point of view, you need four coupling constants for four forces and at least three masses. Then if you look on the cosmological realm, we need to specify the baryon content, which cosmologists call eta. It's famously 6 times 10 to the minus 10 in our universe. We need to specify the dark matter content, which is the dark matter per baryon ratio, which will be analogous to that. Has to be 6 times bigger in mass than eta in our universe, but could be different. We have to specify the cosmological constant one way or another, which we've already talked about. We have to specify the fluctuations of the micro background, which are 10 to the minus 5 in our universe, which we already talked about. And there could be others, but those are the fundamental ones. And I think that another parameter I would put on the table is that when you look at how nuclear fusion actually occurs in stars, it doesn't occur directly. It certainly fundamentally depends on the strength of the strong force and the weak force. But when you do nuclear fusion in the sun, you turn 4 protons into a helium nucleus. 2 of those protons are turned into neutrons, which means you're using the weak force to turn protons into neutrons and you're using the strong force to hold the thing together. There's a net rate that the sun uses to do that whole thing. It happens in steps, but nonetheless, there are nuclear physics considerations that give you composite parameters that are some complicated function of the strong and weak forces.
Yeah.
And we don't actually have a simple theory that gives us nuclear reaction rates in the sun based on those parameters. So you can use a nuclear reaction constant as another free parameter. But if you add up everything I just said, there's something on the order of 10 of them, or maybe 12, depending on how you do your, but there's not 100 and there's not 2.
Right.
Okay. So I would say that you need something like that many knobs. And if you vary any one of them too much, you could imagine the universe would not work, at least not the way it does in our universe, right? And life would not thrive the way it does in our universe. Now, let me say one more thing. Yeah. If we had a fundamental understanding of physics, which we don't yet, and we're working on it, we might be able to calculate the abundance of baryons from a fundamental theory. We might be able to calculate the value of the cosmological constant from a fundamental theory of gravity. So some of those cosmological parameters I put on the table could, in principle, in the future be calculable. And again, we would love to be able to do that, but we can't today, so we're only going to talk about it.
You've written 2 books. I have one of them. I haven't yet got the other one, but I'll surely pick it up after this conversation. You're here to give our colloquium today in the physics department, and I wonder if we could do the thing you're never supposed to do, which is to judge a book by its cover.
Hey, book lovers, we're judging books by their covers. We know we're not supposed to do it, but into the impossible, there's nothing to it. Let's take a look and judge some books.
So I have a copy signed twice by you, the first time 7 years ago, undoubtedly, and then you were kind enough to do it again. So take us away in this first book, and then we'll talk about your other book as well.
Well, I think the story actually begins with the first book rather than the second book. So the first book was called The 5 Ages of the Universe, and it was about the future of the universe. there's lots of cosmology books, including one you've written. Most of them talk about the story of the birth of everything in the universe. So the Five Ages talks about the death of everything in the universe. So that was kind of the, we'd written a review article for physics reports on, not physics reports, some reviews of modern physics on that. And it led to some interest, which led to the book. After that, talking about the death of everything in the universe, the natural sequel was to write a book on the birth of everything in the universe, which is what this book here is about. But there's actually more to the story. The first book on the birth of everything in the universe was called Origins of Existence. But that was the hardback title. When they put it out in paperback, they changed the title from Origins of Existence to Our Living Multiverse. And they decided to do that simply because of something called marketing. They thought they would sell more books that way. And at the end of the book, I talk about a little bit about how there could be more than one universe, and hence the idea of a multiverse. So the book people decided that was a great thing to like use as a hook. So they put a picture of the multiverse on the cover, which is what you asked about, and they changed the title to Our Living Multiverse.
You can show the cover to the camera. The cover, and it's a subtitle, a book of Genesis in 0+7 chapters.
Yes.
I've never seen something described like that. There's got to be a story behind the subtitle. It's more interesting than the story behind my subtitles.
Well, the basic idea was simply that instead of just talking about cosmology, which is great, the Origins of Existence, or this Living Multiverse book, was supposed to have a chapter on physics, a chapter on cosmology, a chapter on galaxies, a chapter on stars and star formation, a chapter on planets and planet formation, a chapter on life, and then sort of a kind of wrap up, big picture kind of, and that adds up to 7. And if you have a little introduction, you get the 0th one. So it was just sort of a cute way to go. It was not as profound as is probably what you're looking for. So,
and what about the other book? Did the other book have a subtitle that's worthy of discussion as well? Or
yeah, it was called The Five Ages of the Universe Inside the Physics of Eternity, because the physics of eternity has some poetic ring to it, according to the book people.
Yeah.
And I don't know if it's changed, but back in the day, we had relatively little say over either the title or the cover.
That's right.
So we wrote the book. So Greg Laughlin and I wrote the first book, and then I wrote the second book just on my own. But we wrote the book, and then they say, well, you can't have the title you want. You can't have the cover you want. This is what you get. Right. So, and that's fine. They think they know marketing. I don't know marketing, so what am I going to say?
Exactly.
And you know, they have to make their money, I guess. Or,
that's right.
Spoiler alert, we didn't make much money. But
yeah, if you ever figure out you want to get depressed, figure out how much you were paid by the hour for writing a book. It's square root of minimum wage at best, if you're lucky.
It's not lucrative.
That's right. Don't go into that field. Or, really being a professor, I would say. Well, one of those processes that you talked about, and I think you alluded to in the PP cycle of the sun, I often hear it's a miracle, right? The Hoyle miracle that allows this, metastable state of beryllium, I believe, to catalyze the eventual construction of 2 helium nuclei. What is that? How finely tuned is that process? Because I've always heard that's a picosecond lasting lifetime on average. And that's one of the pieces of evidence. And even, it's called the Hoyle miracle, right? Is it a miracle?
No. Let's explain that.
Yeah.
To start with, we're confusing 2 things here. There's the PP chain, which is one of the ways in which the sun produces helium. You take 4 protons and turn them into helium, and you get helium out. What you're talking about with the Hoyle resonance
It's carbon.
is the carbon cycle, not the CNO cycle, but rather the carbon production cycle. And there the idea is that if you had 2 alpha particles are helium nuclei. So we call it the triple alpha process. The problem is that if you had a logical universe, the sun would burn hydrogen into helium, then it would have all helium in the core. It would condense, heat up, and then the helium would burn. But the logical way to do it would be helium-4 would combine with another helium-4 to make beryllium-8. And then the beryllium-8 would do something later. But the problem is, beryllium-8 is unstable. It has a half-life of 10 to the minus 16 seconds or so. That's the short number you were referring to. That's a problem. Now, it's not a complete problem because 10 to the minus 16 seconds is short, but it's not 0. So if you imagine that the sun is burning helium into beryllium-8, and then the beryllium-8's decaying in 10 to the minus 16 seconds, the sun's going to keep taking those heliums and making them back into beryllium-8. So it's like juggling. There's always going to be somebody in the air. There's always going to be a standing population of beryllium-8, even though its population is small because its half-life is so small. So that beryllium 8 during its brief moments of existence can interact with another helium nucleus and make carbon, because carbon is carbon-12. It's basically 3 alpha particles, 3 helium nuclei glued together. And once you've got carbon, it's stable. We need carbon for life. We're good, right? So the problem is, do you get enough carbon? Now, historically, saltpeter realized that this standing population of beryllium-8 would be enough to give you carbon, but there wasn't enough. And then Fred Hoyle said, well, wait a minute. I will just make the reaction rates big enough to give me enough carbon. He just said it. Then he said afterwards, well, I wasn't around at the time, but this is the after the fact telling of the story, right, that I'll come up with a reason to have this large value. And the reason is there's a resonance. And if you put the resonance at the right level, right energy level, resonance is just an excited state of the nucleus, then you can make the reaction rate to produce the carbon go faster. Mm-hmm. And if you make the resonance at the right level and make the cross-section bigger, you get the carbon we see. So Hoyle famously predicted that there would be a resonance in the carbon-12 nucleus that I believe the story is that Willie Fowler at Caltech then discovered it, yeah. And it's super important for the way our universe works and the way our universe makes carbon. Mm-hmm. Now then, the question becomes, if I change the value, the energy level of that resonance, yes, what happens? Well, here's the thing. And people have said, well, if you change it a little bit, you change the carbon abundance, which is true. Yeah. But let's do the calculation. So this is a hard calculation, so I had an undergraduate do it. She was actually a very smart undergraduate named Lillian Huang. She and Evan Groves, who's a graduate of here at UCSD,
yeah. I was on this committee.
Did this as her senior thesis. And what she did is she ran the MESA models to do carbon-12 production in massive stars over a huge mass range and a huge range of resonances. Bottom line is, the first thing you need to know, if you make the carbon resonance lower energy, you get more carbon, not less. So you can get a better universe with more carbon if you change it in one direction. But as you make the carbon resonance higher and higher and higher, you get less and less carbon out of your stars. But here's the thing. It's not that you don't make carbon, or that the stars don't make carbon. The stars make carbon, but because they're burning so hot, because you've raised the resonance level, the carbon will immediately or tend to eat another alpha particle and become oxygen. So you're replacing your carbon with oxygen. Now, then the question is, how far do you have to go before you don't get any carbon out?
Right.
So it turns out you can move the resonance in physics units about 300 MeV down and 500 MeV up and still get carbon up. So you have a range of 800 MeV. Now, what the heck does that mean, right? Well, one thing you need to know is that the resonance levels in nuclei are typically only a couple MeV apart. So this is a good fraction of the distance between them.
The total energy.
The other thing that you need to know is that the whole reason the stars have to jump through these hoops and produce carbon through this triple alpha process, as we call it, with this resonance, is because beryllium-8 is unstable. But it's only unstable by something like 92. I said MeV, I meant KeV earlier. So,
but the level of this energy level is at the MeV level, but it has width. The resonance has a width of the KeV. It's 1,000 times smaller.
Sorry, I misspoke. So let me start again. Mm-hmm. If you look at the broad picture, you can move the resonance level about 300 keV down and 500 keV up. So the range is like 800 keV, which is a good fraction of an MeV. Yeah. And the typical spacing of nuclei resonances is measured in MeV. Usually they're only 1 MeV apart, but in carbon they're a couple MeV apart. So the range over which you can have valid triple alpha resonances is a healthy fraction of the spacing of them. The other thing you need to know is that if you look at beryllium-8, the beryllium-8 only fails to be stable by 92 keV. So here's the thing. 800 keV is bigger than 92 by about an order of magnitude. So in a certain sense, it's 10 times easier to make beryllium-8 stable and not need the triple alpha reaction than it is to change physics so much that the triple alpha reaction doesn't work.
In terms of fine-tuning,
so do you call that? It brings us back to the question we raised earlier. You know, the story is complicated. Is that tuning? Is that not tuning? It's not that sensitive, but how do you place a number on the tuning? Mm-hmm. That also leads us to another thing that I think we need to put on the table in this discussion, is that we have been talking as if we can, in our theories, change the value of the constants, change the value of the triple alpha resonance just as we feel like it. Right. And we can do that calculationally. Right. But the question that underlies all of this is, what's the probability distribution from which these constants are drawn? Mm-hmm. And here we have a problem. We simply do not know. Yeah. Now, when people do probabilities, they have to assume something. But it's important to know that people are simply assuming a probability distribution. They have no idea that that's the probability distribution. Right. We have no fundamental theory that gives us that probability distribution. Now, you can make an argument, well, it has to be logarithmically distributed, or it has to be uniformly distributed. Both of those answers will give you completely different probabilities over these enormous ranges that we're talking about. And you can make both of those arguments, but we don't know if any of those are true, right? So one of the fundamental things about this whole enterprise is that we don't know what the underlying probability are. So what I would say is, and the tack that I've taken in the things I can present in the talk today, is that in the absence of knowing the probability distributions, the first step is to simply see what the range of values is. How big can we make, or how big a range can we make the parameters vary and still have a working star or a working nucleus or a working galaxy or whatever it is that you ask, right? So the first step in the story is to get the ranges right. And that's, to my mind, about as far as we've come.
And even pushing farther back, so making a star, making a planet, even more primitive than that is, many time past guest Sir Roger Penrose has pointed out the initial value of the universe's entropy must have been extraordinarily low.
Right.
How does this factor in? Is this going to be a part of an initial conditions or boundary conditions problem that has to be solved in addition to the 10 parameters that we already discussed? Or is it something completely literally in another universe that this is bring up questions not related to the type of fine-tuning that you're talking about? Is it a fine-tuning problem to say that it was close to zero as we can possibly speculate?
When we look at the very, very early parts of the universe, and we look at what I would call the moments in which the universe is launched, at those moments, there is an issue. We can call it the entropy problem, and I respect Penrose, and I'm happy with his framing of the question. All good. But the picture that emerges to me is that somehow when the universe launches itself into existence, however it does that, and I should remark, we do not have a fundamental theory of that yet. That's right. Again, one of those things we would love to be doing.
We're working on it.
We're working on it. But I don't think we have a credible theory of that yet. Right. But somehow the universe does say, well, this piece of space-time is going to separate out from whatever manifold its parent is and start expanding. It's going to expand rapidly enough to become old and big and flat and homogeneous and isotropic like our universe. Now, one part of that story is probably the inflationary universe. Right. That when the universe is cooled from the Planck scale to the Guts scale, so 10 to the minus 37 seconds old or so, it somehow gets itself caught in this state where its energy density is vacuum dominated and it's in an accelerating state. And if it finds itself in that realm and accelerates long enough and then successfully gets out of it and reheats, then we get back our universe. So I think that there is an important problem in the very, very early universe, the ultra early universe we're talking about, of how does a universe come into existence and launch itself from its parental space-time manifold, and how does it get into inflation or whatever replaces inflation? I mean, you always have to say, well, inflation isn't 100% proved by any means, so there's alternates to it.
Yep.
I happen to think in terms of inflation, and Alan Guth was my office mate for a semester, and I had the privilege of writing a paper with him, so I'm very much in favor or want the inflationary picture to be a good part of the story, but that doesn't mean that it is.
Sure, right.
We have to keep all these possibilities in mind. But I would say, the way I would say it, is that if inflation isn't the thing that makes the universe big and flat and homogeneous and old, then something like it does. So I will say inflation is something like it has to happen. So to back up, there's an issue of how you launch a universe and go into an inflation-like state. After that, you get a universe that may or may not be alive. And it's at that stage where I begin
calculating entropy, getting back to the entropy.
Well, at that stage, you're good on entropy because you've already inflated.
Right. So
yeah, you've already solved the entropy problem, and you're just big and old and going to expand for a while, then the question is, do you make structures? And structures can be heavy elements, starting with helium, on to carbon and other heavy elements that are more interesting. And do you make stars and planets and galaxies and all the structures that we have in our universe? So those are the questions that, as an astrophysicist, we can actually do calculations on and say, well, what range of the fundamental parameters will allow us to make all of those different kinds of structures. And that's what we can actually do an honest calculation of.
We've had on multiple believers and different forms what would be considered intelligent design supporters. One of the things I hear a lot about from guests that have been on that are proponents of so-called intelligent design, Stephen Meyer, Luke Barnes, others, is that the claim that our universe is not designed or optimized for life, is sort of an attack perhaps on a designer. If you don't have a need for, if you're not actually finely tuned, finely designed, then it obviates the need for a designer. And, so the question that I often hear from them is that, well, who are we to say what a designer would or wouldn't do if they have the power and capability to create a universe? I mean, Sean Carroll has said, things I find ridiculous, like what's the purpose of all those galaxies in the Hubble Deep Field? Okay, so they don't do anything for you, and therefore they're meaningless, and that's evidence against the God, because why would God create so many galaxies? Well, you could have said, in the year 1850, why do we need more than 32 elements that Mendeleev had in the periodic table? And now we know that a lot of them are necessary for life beyond what we actually think, or just for the conditions of life. Radioactive decay heats the Earth's crust and provides it with a temperate environment. We didn't know any of that back in the 1850s. So isn't it a little bit of hubris to say what would a designer or what would not a designer view as criteria for their creation, his or its creation of the universe? What allows us to say what would be a better choice of parameters or of tuning ability and whatnot? How do you react to those common kind of concerns? I'm sure you've heard them.
First of all, let me say that I don't want to step over or step upon anyone's beliefs. And the question of whether there's a intelligent design or whatnot as an argument for the existence of God is not something that I'm going to address. And the reason is not that I'm a theist or an atheist. It's more that I'm a heathen.
So you would have obligations under a system where you knew for sure there was a God, or believed with evidence.
No, and by that I simply mean it's not what I'm about. The question itself.
It doesn't interest you.
It's not a relevant question to my work. What I do in my own time when I'm not working is none of your damn business. But it's not relevant to the science that we're talking about. Both in the question of anthropic arguments and intelligent design arguments, they both have something in common, namely that they say, well, if the universe were a little bit different, it wouldn't work. And then the intelligent design argument, in a nutshell, as I understand it, again, I don't work on this, is that if it were a little bit different, the universe wouldn't work. Therefore, someone designed it very carefully. We need a designer. And that designer is presumably a deity. Yeah. And then the anthropic arguments say, well, if you change the constants a little bit, then the universe wouldn't work. Therefore, the fact that they have the values they do, that the constants have the values they do, is an argument for why they have the values they do. It's at least a consistency argument. Both of those fundamentally rely on the idea that if you change the constants a little bit, the universe doesn't work. So I think, again, back to what we said earlier, the first step in the chain is to ask the more fundamental question, the starting question, what range of parameters work? So that is the question that I'm interested in. That is a question that I have worked very hard to try to answer in a variety of ways. That is exactly the subject of my talk this afternoon.
Yes, which we will air after this one.
I've written 12 papers on this in hopes of answering parts of those questions. And I think that unless you find that the constants need to be very fine-tuned, that they have to be in very small ranges in order for the universe to work, unless you find small ranges, then anthropic arguments carry very little weight. And the intelligent design arguments don't carry very much weight. But let me just say right away, I think if you want to be a theist and believe in, we'll say God, you don't have to believe wrong things. You can believe in God without believing in intelligent design. You can believe in God without making incorrect arguments about intelligent design. Many of the intelligent design arguments that are online say wrong things about what fine-tuning arguments do. They say that if you change the strong force by a little bit, then stars don't work. It's simply not true.
Just before we wrap up, I want to make sure that you hit subscribe and join me beyond the Big Bang every week right here. Click to subscribe and make sure to leave a thumbs up. And for bonus extra credit homework, leave a comment.
But
what is their strongest argument? What would be the one parameter that is the most finely tuned? I don't think I actually asked that
so
question.
if we back up to that, you could ask the question.
Steel manning them.
Okay.
Yeah.
What's the failure point of the universe? In other words, if I want to turn all the knobs, strong force up, strong force down, gravity weaker, whatever, what's the easiest way to kill the universe?
Right.
The answer is, if you look at our universe and we look at something as simple as the hydrogen atom. The hydrogen atom consists of a proton with an electron in orbit around it. In another scenario, you could imagine that in our universe, the neutron is heavy enough that the proton and the electron in the hydrogen atom cannot combine to form a neutron because there's not enough energy to do so. Mm-hmm. But if you change the masses of the quarks enough, then you can imagine the mass difference between the proton and the neutron being smaller than the energy you have from the electron, and that you could imagine a hydrogen atom being unstable. And if that were the case, then our universe would be very, very different. And that failure point, making hydrogen atoms unstable so protons eat their electrons and become neutrons, that failure point is the closest our universe is to failing. In
so
parameter
it's a few
space.
MeV out of 1,000.
Yeah.
And actually, you'd only have to change one of the quarks. You only have to change the down quark, right?
Now, to be clear, if you look at the whole range of allowed quark masses that work, we just happen to be close to the edge of that parameter space. You can move the up quark several orders of magnitude lower and still have the universe work. And for most of that space, you can move the down quark, not quite an order of magnitude, turns out to be a factor of 7 up and down. So there's a wide parameter space of up-down quark mass space that works. It's just that we happen to be very close to the edge.
Yes.
So if you move it downward a little bit, you can go into this failure point where electrons and protons get together in hydrogen atoms to make neutrons and no longer be hydrogen. So that's our failure point. At least I should qualify that. That's the closest failure point that I've
That's the most finely tuned.
Well, that I've discovered so far. There could be one that we'll find tomorrow, or someone else who's smarter than me will find as well. So that's just as good as I have at this moment when you're asking.
That's
me.
intellectually
I just want to
honest.
qualify that. So
You're being intellectually honest, which we expect. So the last topic I want to bring up always seems to come concomitantly with discussions of tuning, et cetera, and that's the multiverse. I've had on Andre Linde, in the past, and he, almost yelled at me. I mean, he's a gentleman, but why do you insist on a universe? Why should I be defending the multiverse? Shouldn't it be you defending the universe to me? What do you make of these arguments? Is the multiverse more natural than than a single universe? And what role, if any, does it play in fine-tuning arguments such as those that you work on?
Well, I would say that, to my mind, having more than one universe is, in fact, natural. Going back to our earlier discussion, we said, well, how does the universe begin? Well, somehow it launches itself into existence by taking a little piece of space-time that separates itself out from its parental manifold of space-time, and that little piece of space-time that becomes our universe somehow starts expanding, maybe by inflation, exponentially rapidly, making it low entropy, reheating to our Big Bang picture, etc. But if we describe the birth of our universe that way, there's absolutely nothing to say, well, why does it happen only once? Why can't another little piece of space-time do its own version of that story? And if one can, why can't more? So I think it's perfectly natural, given the way we describe the birth of our universe, for there to be birth moments of other universes, other space-times. And just logically possible, it's logically possible that these other space-times get launched into existence and expand in their own spaces and never interact with ours. And it's just perfectly possible. So it's certainly possible. That doesn't mean it's got to happen, but it's certainly possible. And in my own, I think, bias is simply that if it happens once, and if it happens according to the way we tell the story, then it's natural it would happen more than once.
Can you falsify that hypothesis?
So the way you falsify any such thing is you say, well, we can't directly go to the other universe, kind of by definition. We got a problem there. But let's say, let me give you an example. We say that the sun's going to turn into a red giant in 7 billion years, right? And when I say that, you don't say, well,
let's wait around and see.
How do I know that? Are you sure your theory is right? Can you falsify that? No one gets on their high horse and gets all bent out of shape when I make a prediction like that, even though ain't nobody going to be around in 7 billion years to see that happen. It's not going to be verified.
There's this guy, Brian Johnson, who's working on longevity. We'll see.
Yeah, well, that's a separate issue. But why do we believe that? Well, the reason we believe that is that we have the equations of stellar structure, and damn it, they work. And we can describe, not perfectly, but we could describe the structure of the sun, we can describe the structure of other stars, and we test that theory. We test it in the sun, we test it in other stars. We have our stellar evolution codes, they turn into red giants, and we watch red giants in the sky, and we verify, and we verify, and we verify, and we have this theory that works. And because we have this theory, it works, and it's a damn good theory, this theory of stellar structure. Yeah. Because we have this theory that works, when we say, well, when we apply it to what our own sun's going to do in 7 billion years, I have a little bit of confidence that that's not exactly, but pretty close to the right story. Okay? So, suppose this whole enterprise of string theory and its descendants like M theory becomes successful, and it's a complete self-consistent theory of everything that describes everything in our universe. Yeah. And suppose further we can verify it. Now there are ways to verify that. It would predict something about proton decay. Yep. And if we have a big enough proton decay experiment, we might be able to measure that. It will explain something about the highest energy cosmic rays, and maybe we can see a quantum gravity effect in cosmic rays. I mean, we don't have any of these things, but you could imagine that you have a good enough theory of quantum gravity, string theory, M theory, that you could make predictions of things like quantum gravity on cosmic rays, proton decay, etc. And suppose it worked. And all those things, like, suppose it got to the level that the standard model of particle physics is now. Suppose further that fundamental theory, which is now, in my mind, verified, or in my scenario, verified because we've done the experiment. Suppose it also predicts the launch of the universe, and that an inevitable consequence is that there'll be launches of other universes.
That's right.
Then you still wouldn't have experimentally verified the launch of another universe, but you would have a theory that's battle tested that predicts that, and you would have some confidence that there would be other universe launches the same way we have confidence that the sun will turn into a red giant. Yeah. We would need the quantum gravity theory to be on the same experimentally verified foundation that the theory of stellar structure is. And if you could achieve that, it'd be wonderful on a lot of fronts, right?
That's right.
But that would allow you to predict or be confident of the existence of
plausibility.
The plausibility. Right. It wouldn't 100%, never say, it's never 100%, science is never 100%, right? But it would give you a whole lot more confidence that that's a reasonable thing. Yeah. We are a ways away from that, to be honest, right? Of course. We are, because we're a ways away, you kind of have to hope one way or another. So you kind of hope, well, it kind of makes sense that there should be other universes, and I kind of like that idea.
It's in the Copernican argumental chain,
Yeah, it's the natural step in the degradation of our places, right?
And that's right. I call it the ultimate cosmic big brother principle, that you're not that special. Yeah. No one really cares about you. Well, Fred, thank you so much for being here and for the talk that's going to be so spectacular. I want to give you a byproduct of stellar evolution here. This is a real-life meteorite, which you will get to out there if you have a .edu email address, as Fred does.
This thing's heavy.
Yeah, it is heavy, and it's highly magnetized too. Yeah.
So that's actually important. Yeah. You're going to demagnetize my hotel card?
No, it won't. The hotel card might no. It will not do anything of the sort. It's not that dangerous. It has a little bit of radioactivity in it, but so do bananas, right? Yeah. So I give those away to people that join my mailing list, briankeating.com/list. But if you have a .edu email address and you live in the US, I can send them to you. So go to briankeating.com/edu for that free gift that will come your way, not via gravity, but via the U.S. Postal Service. So, Fred, this has been great. Give a 1-2 sentence blurb about the talk that my audience is about to hear, which is your colloquium later today at UCSD as a physics colloquium.
Well, the idea of the talk is to actually do or present the results of the calculations we talked about. Namely, if you consider the universe to have a number of parameters that could in fact vary from universe to universe, you can ask the question, what ranges of those allow for working structures? And by working structures, I mean anything from nuclei to planets to galaxies and stars and such.
If you want to go even deeper into cosmic fine-tuning and hear an alternate take, the case for and against the multiverse, check out my conversation with astrophysicist Professor Luke Barnes. It's one of the most mind-expanding conversations I've ever had. Watch it next.